Hi everyone, and thank you for watching my talk. I'm very happy for this initiative by the Virtual Axion Institute, and I want to tell you a little bit about a project that I just did at Brown University with Professor JiJi and with Chen, who used to be a postdoc at Brown and now is at Tel Aviv. This is a recent paper. Here's the archive number. It's going to see it through the slides, and it's about constraints on axions from cosmic distance measurements. So first, a word of interest, perhaps. I have another talk in the same space called Dynamical Axion Misalignment with Small Instances. So do watch it if you find it, if you think you're interested. Here's the archive number. Go and read it. Thank you. Okay, so let's talk. In most axion and axion-like scenarios, there are couplings between axions and photons. So as a result, there's a very interesting phenomenon that can happen, and that is it's the one of axion-photon conversion. So if you have a very attentive observer and a source of light emitting photons, what could happen is that in the presence of a magnetic field, an external magnetic field in the path of these photons traveling from the source, you have a certain probability of the photons converting into axions because of this coupling between axions and photons that's given here on the bottom right. As a result of this, some of these photons will convert into axions, and that means that at the end of the day, you end up with less photons that you started with. So you have your source emitting a bunch of photons, some of them convert away into axions, and you end up with this. This is called, unsurprisingly, dimming. So some photons are converted into axions, and what can happen then is that you can get fooled into thinking that the source is farther away than you would initially think, because when something looks dimmer, you can think it's farther away. So it's an interesting phenomenon, that of dimming through axion-photon conversion, and we can go ahead and test it and see if we can put bounds on axion-photon couplings. And a particularly interesting playground to do this is space, because there's a bunch of different light sources, and there are magnetic fields in space, and we have a way to measure distances in space through general relativity. So it is a very interesting playground in which we can try to look at this, right, and see if we can put bounds from cosmic distance measurements. So first of all, a word on magnetic fields. There are magnetic fields in our galaxy. Measure them. There are magnetic fields inside clusters of galaxies. Measure them. It is hypothesized that there are also magnetic fields in the IGM, or intergalactic medium, which is basically the vast distances between large structures, and they can have different origins, from inflation, phase transitions, or outflows of galaxies. They haven't been quite measured, but it's expected that they're there, and commonly used benchmarks is of order nanogauss for the strength of the magnetic fields. So keep that in mind. One cosmic distance that we can use to try to prove axion-photon conversion is that of luminosity distance, in which you have an object with a very well-known luminosity, and you go ahead and measure the flux of light from that object at your position as an observer, and from there you can infer the distance that object is far away from you. This is called luminosity distance, and it's because the flux scales like 1 over the radius square, right? This luminosity distance will be cosmologically dependent. Depends on Hubble parameter and how much matter there is, etc., etc. And this is a standard view in standard models such as lambda CDM. However, if you have axions, you need to worry about some of these axions converting away into photons with a probability we just know about, which means that only a fraction of those initial photons will make it to the observer, right? So at the end of the day, you end up with a flux that is suppressed by a probability we call survival probability of the photons. That is the probability of a photon to make it all the way from the source to the observer. And this is a number smaller than 1. As a result, you end up with an effective luminosity distance, which is given by the good old luminosity distance from before, but suppressed by this, but divided by this square root of the survival probability. So this is a number smaller than 1. You divide by that, you end up with a larger number, which shouldn't be surprising, really, because what this is doing is dimming the source, which means that the distance inferred from this method will seem to be larger, right? So here's a nice plot on the x. This is the same formula as before. On the x-axis, I have redshift of some source. On the y-axis, I have something called apparent brightness. It is basically the log of the flux from the sources. And the sources here, the data points, are 1048 supernovae in the Pantheon dataset, supernovae type 1a. And here on the color lines is the effects on the luminosity distance from axions. So you would have a value, this is the effect from axions with a coupling of 10 to the minus 12 GeV. You can basically see that it agrees with lambda CDM. That's what 0 means. But a much larger value, an order of magnitude larger, 10 to the minus 11 inverse GeV, coupling of axions to photons, that gives a very strong distortion on the luminosity distance that end up missing a bunch of points. And you can use this then to put bounds on the coupling to axions. Now, another distance you could use is called angular diameter distance as opposed to luminosity distance. And this is basically measuring how far away an object is if you know the size of its physical size and the arc it subtends in the sky. So there's some very clever people figured out a way to do this for clusters of galaxies. And it is very interesting. I don't have all time to give you all the details, but it basically consists of looking at the cluster with your X-ray lenses and looking at the cluster with microwave lenses, and the ways, your glasses. And the way this works is by looking, for example, at the cluster in X-rays and measuring the intensity I of photons coming from the cluster in X-rays, and then also comparing with the intensity of the cluster shining in the microwave. And this is through something called the Sunyaev-Zeldovich effect. So basically, it's microwave photons from the CMB scattered off of the cluster, which ends up producing a distortion on the CMB that you can quantify as an intensity, right? So there's microwave photons and there's X-ray photons. You combine them in this way. You calculate the angular diameter distance to the galaxy cluster in the standard lambda CDM model. If you have axions, you need to, again, worry about some of these X-rays not making it to the observer. So you need to multiply by the survival probability. And then you need to worry about some of these microwave photons from the Sunyaev-Zeldovich effect not making it to the observer. So you need to multiply by the survival probability of this. So at the end of the day, you have an effective ADD, angular diameter distance, that is depending on the good old angular diameter distance you would expect in lambda CDM, multiplied by a bunch of factors from survival probabilities of the photons in X-rays and microwave. So similarly as before, we have, therefore, you can make a plot of what the effect of axions is on angular diameter distance measurements to clusters. So here's a data set by this very same clever people, Buen-Abad et al. And this is gray dots. And here's the effect on the angular diameter distance from axions. You can, for a sufficiently small coupling, the dimming is very small. But for stronger couplings, you end up with a significant distortion, right? And similarly as before, missing a bunch of points, thereby setting a bound on the coupling of axions to photons. So that's very nice. We can then put these data sets together and then consider the parameters from lambda CDM and axions, like such as the coupling or the axion mass, and fit these parameters to the data and see what values of the parameter space from the axions are ruled out. We consider supernova data sets from Pantheon, clusters from the Buen-Abad set that I showed you, consider BAO. We also consider measurements of Hubble node, which is one of the parameters, from either Schuss and TD Cosmo or Planck, which, as you might remember, you might know, they are in disagreement. So we do different independent runs. We consider different IGM properties and something that I'm going to tell you a little bit about, and which is conversion, the possibility of conversion inside clusters. We scan the parameter space and we get our results. So here is the axion parameter space, and the mass of the axion in electron volts and the coupling to photons, inverse GeV. In gray, here's a bunch of bounds from other measurements, such as CAST or supernova 1987. And in color is our results. So please ignore for now the blue lines. Let's focus on the red lines here. So what we have here is what I have been just telling you about, in which the conversion of photons to axions, the dimming of light sources through axion-photon conversion, happens en route as the photons propagate from the source to us, the observer, right? And that's the only effect we worry about, and this is what we get. Now, the solid line is what you get in the bounds if you consider Hubble parameter H0 from cosmology to be given by the value from Schuss collaboration from Rees et al., which give a 74 kilometers inverse second inverse megaparsec value. If, on the other hand, you consider the value from Hubble to be given by the Planck collaboration, which gives 68, I believe, you end up with this dashed line. Now, if you remember, like I was telling you about, these two collaboration gives values of Hubble, 74, 68, that are in tension with each other. This is called the Hubble crisis or the Hubble tension, which is all the rage right now in cosmology, and it's very interesting. But what you can see here is that outer bounds are basically independent of what you're choosing as the H0 value, either choose or Planck. It doesn't matter. Our bounds are independent of the Hubble crisis, whether there's a crisis or not, and whether it's solved or not. Why is that? Well, it turns out then that our bounds really do not depend as much on the absolute value of the distance as much as on the shape of the distance as a function of redshift, right? The functional dependence of Hubble or the distance as a function of redshift. That is really what the axions can affect, and our measurements are sensitive to. Right? So that's very nice and dandy. That's for the red lines, solid versus dash. There's this blue lines, which is an effect that I didn't have enough time to tell you about, but is that just as you can consider photon-axion conversion en route from the source to the observer, you can also consider photon-axion conversion inside the clusters, because there's a plasma there, there are magnetic fields inside the clusters, and you can go and consider this. These are subject to some debate currently. You can look at these references, but if you consider this, there's an extra suppression on extra dimming of the light from the clusters, right? The X-rays from the clusters, which boost your bounds on the coupling of the photon in the axion. So this is the blue lines. And similarly, whether you trust the Rees value for H0, or whether that's the solid line, or whether you trust the Planck value, and that's the dash line. So just to conclude, for masses of axions of smaller than 10 to the minus 12 eV, as I show you, you have very strong bounds, very competitive bounds on the gauge, on the coupling of the axion to the photons. For some common benchmarks of the intergalactic medium, the magnetic field there, 1 nanogauss. You can talk about this. You can look at the references there. Our results are independent of the Hubble crisis. Doesn't matter what H0 is. Really, what matters is the shape of Hubble or distance as a function of redshift. Now, if you include effects in the intracluster medium inside the cluster, you get even stronger bounds, right? These are subjects to some debate, some uncertainty, but it's very interesting. And how can you improve this further is if we have better measurements of the shape of Hubble as a function of redshift, or also if we can determine better this ICM and IgM magnetic properties, such that we can have more confidence on these bounds. And this is all I have. Thank you very much for your time, and I hope you enjoyed this.